Okay, this lecture will be doing parlor tricks, things you might have seen, gifts you might have gotten, cool little physics things that are around that you might, if you're at a party or something like that, you might have seen this. They're kind of fun. So I'm not going to go into detailed explanations, but I'm going to talk about them a little bit. So this is Extraordinary Concepts in Physics, sometimes called Physics X. I'm Robert Nemeroff. This is Michigan Tech. This is an actual class being taught. There's maybe 50 or so of these lectures on the web and iTunes, and you can find them here. And you can search for terms. There's a lot of fun stuff. I advise you to go look. So, does this remind anybody of anything? So this is called Newton's cradle. I don't think Newton had such a cradle. I've occasionally gotten this for gifts, and which, you know, people mean well. I'm not sure what they're trying to show me. But this happens, everyone's seen at least one. Ball goes back and forth here. You pick it up, you drop it, and the ball goes off the other end. And the question is, how is it that these balls know to stay still? And you know what? If you take two of these and you move these back, then you get two of these going off. How does it know? Kind of strange. It shows, however, that there is conservation of momentum. There's conservation of energy. So momentum goes like mv, mass of the balls dropped, times velocity, particularly when they're at the lowest level. Conservation of energy, so when there's a collision it would be conservation of kinetic energy, but the kinetic energy gets stored in potential energy as the balls rise and then falls back down. So you have to conserve both of those. And when you do that, you see how many balls should leave. So in that sense, this is pretty well understood. However, it gets a little more fuzzy when you realize that sometimes, particularly when there's more than two or three balls, that there are solutions that are more than one solution could both conserve energy and momentum, and that isn't usually discussed. To break the degeneracy as to what happens there, you have to understand that there's actually a shock wave that moves through the metal balls. And that takes a certain amount of time, and that breaks some possibilities that might have happened. It does show conservation of momentum energy. However, if you had a three-ball collision, you know, and balls would go off in some ways, you would ask, why do some balls go off in some directions and some go off in other directions? And the answer to that is conservation of momentum and conservation of energy in different directions. And so it's really no different. However, I'm unaware of a really highly detailed analysis of how much force is transferred between the two balls that both go off in one direction. So I'd like to see an accelerometer or something or put between them to really show how much goes and how fast the shock wave passes and what exactly happens. So there's even in common desktop examples, I think there are things, there's a frontier of physics even there of where interesting things can be learned. So here's a good one. So when I saw this thing, I was, can an object spun in one direction, stop spinning, and then start spinning in the other direction? So let's say you take your cell phone and you spin it. You put it on a table. Here's a table. You put your cell phone down on the table and you spin it around. Is it possible that it could stop spinning and then start spinning in the other direction? Oops. So it stops and then it goes back in the other way. Can that happen? Yes, that seems okay to me. No, that does not conserve angular momentum. Or, we're sorry, the number you've reached is not in service. So, drum roll please, the answer is yes, that seems okay to me. This occurs for a common type of stone called a rattleback. And when I saw one of these, I just had to stop whatever I was doing and just play with this rattleback for a while. And now I have some. I used to have one in the office and I would have brought it down here. Oh, just a second. Please forgive Google Docs. You can order these rattlebacks over the inner tubes now. So the way they work is very interesting. They're not perfectly symmetric, and so they look like this in profile. And you spin them, put them on the table here, and then you spin them like this. And what happens is, after a while, their asymmetry causes them to bobble up and down, and then stop and go back in another direction. And these are made of cheap plastic. Before that, people knew of them in terms of stones. Stones were carved very specially, and they were also wood carved. And actually, the science of exactly what three-dimensional shape will create a rattleback is again a frontier of physics and is being and you can go into detail on almost anything. However, since I didn't bring one, I can show you a video called the Rattleback Oddity. So you can get them from any number of places. Ignore the advertisement if you want, and there it is. It's just going back in the other direction. It starts in one way, it goes back the first way. So what's happening, stop, hello, oops, we'll get to that. What's happening though is angular momentum is conserved. What's happening is that angular momentum is being transferred between the table or the top that you put it on, the place that you put it, and the small device itself. So if you were to take this and throw it in a vacuum and spin it in vacuum out in the air, if you just threw it in the air and spun it, it would just continue orbiting because that would conserve angular momentum. However, just like your car is sitting there, and then when you push the accelerator of your car, it starts moving, where did the linear momentum come from? It just started moving. Isn't that crazy? Well, the Earth is absorbing the linear momentum in the opposite direction. Just like the rattleback transfers angular, pushes on the table and pushes it back in the other direction. So the table, if you were to have a frictionless table here, frictionless ball bearings, and you put a rattleback on there, and you spun it, you would find the rattleback spins in one direction, starts spinning in the other direction, and the table will then go back in the other direction. So the table will spin with the opposite angular momentum of the rattleback. But because the table is affixed to the floor, just like your car is affixed to the road, you don't see it. Okay? Oh, come on. Okay, the next thing that's very popular is the drinking bird. How many have seen this one? So it's a toy. For a while, when I first became really interested in these, I saw one, I wanted to get one, and I couldn't find them anywhere because they started getting worried that the fluid in here was dangerous, and it was. And it still is a little bit. So here's your advisory. Don't drink that fluid. It's not red water. Don't drink it. Still, if you're careful not to break it, and hopefully this is plexiglass now and not breakable glass, you can see these things work. And they are cool. So here, I'll show you the movie first. Let's go. So the dunking bird bobbles back and forth for a while, and then it's going to put its head into this thing. Oh, then it's going to sit up again. And these four symbols, they're irrelevant. And so the color of the fluid is irrelevant, and it's going to keep going. It's going to do it again. And this seems like a perpetual motion machine, which is a lecture that was just done. It is not perpetual motion, however. It is somewhat well understood what goes on. It involves a lot of thermodynamics. And I'm not going to go into detail because it is really complicated. But the drinking bird is effectively really a heat engine. It doesn't generate energy. The mechanism is complex, as I said, but it hinges on the liquid that's inside, which, well, actually on outside too, because water on the outside does two things. It evaporates from the head, and it's also usually the water is a little bit colder than the surrounding air. But my understanding is this can work even if the water is the same temperature. It just works more efficiently if it's colder. Also, you can heat the other end with a lighter or something and get the same effect. Evaporation is a cooling process. Things cool as they evaporate. So the temperature on the different sides of the dunking bird are slightly different, and that drives heat processes where fluids and air is transferred between the two as temperature tries to equilibrate. So the power source is effectively the water that's evaporating from the outside, and the cold water could be a power source, or the heat on the other end could be a power source, or the water that's evaporating just from the head is a power source for this thing. So they're not getting free power. Okay, this is a good one. So I stumbled on this when reading a Feynman book, which I sometimes do for fun. So you have a circular string on which electrically charged balls are affixed all around, and you drop a magnet through this string. So what happens? So here you have the string in a circle. Here's the spin axis. And these are electrically charged balls. Let's make them negatively charged. Let's say you can use balloons or something that are negatively charged. So these things so then you have a magnet which will miraculously become blue. And this magnet has a north and a south. And you drop it straight through here. So the question is, what happens? Now, is it the string and balls begin to rotate in one direction and the magnet rotates in the opposite direction? Is that what happens? Do the string and balls begin to rotate in one direction but the magnet does not rotate at all? Do the string and balls begin to rotate in one direction and the magnet rotates in the same direction? Or does Uncle Tesla call and ask you where you got this idea? Because as you might be familiar with Nikola Tesla, he'd be proud of this device. Okay. Please don't be upset if you don't get this right. This is a strange one. You might take this opportunity to call the friends back that you just called and apologize for what you thought was the answer and come up with a new answer and tell them the new answer. Okay? You could put it on pause and wait till you're older and start it. Okay, now you're older. Ready for the answer? The string and balls begin to rotate in one direction, but the magnet does not rotate at all. So this is discussed, so make sure I'm not making this up, in Feynman's book, The Character of Physical Law, and you can turn to page 78 and see it there. What's going on? Does this conserve angular momentum? It doesn't, you might say. It's not a closed system. Maybe it's like the rattleback. Considering the charge, the balls themselves actually carry no angular momentum. If you consider the charge there too. Okay? The electromagnetic field generated carries the opposite angular momentum to the rotating balls. Or who cares, because peculiar situations like this are irrelevant. Why are you worrying about this? Drum roll, please. The electromagnetic field generated carries the opposite angular momentum to the rotating balls. Fields, electric fields, magnetic fields, things like that, they can carry angular momentum and they can be exchanged. So it looks like if people just think of angular momentum just being things going around in circles and carrying mass, but fields can carry it too, as strange as that may sound. And with that, I will conclude this little bit lecture and ask you to keep Schrodinger away from your cat.